Like I said, we started with this information last class and we took a poll around the classroom to see this information. And we're going to use it today to explore the concept of independence of events. So events can be deemed to be independent or dependent depending on how that they are. So we need to understand what that definition means. To do that, I'm going to lead you through a set of questions to kind of arrive at our definition for independence. First part here says, given that the person selected, that we're randomly picking from the class, is a yes evil eyebrow, what is the probability that they are a yes taco tongue? Now, last class when we did all of our probabilities for evil eyebrow and taco tongue, we were using the total of 27 students in the class. Once that phone rang, I kind of lost track of my thoughts, so I might have to start over. We're given this time that the person selected out of our class, we already know they can do evil eyebrow. How many total people in our class could do evil eyebrow? In total, 10. Now, that means that my total number of students that we're pulling out of is no longer 27 from the class in total. We already know that they're yes evil eyebrow, so it's out of the 10 who are yes evil eyebrow. It says, what is the probability that they are a yes taco tongue? So how many of these people could do taco tongue? Of the 10 that are yes evil eyebrow, how many were yes taco tongue? 10. 10 out of 10, that's 1, which is 100% of our class. Going on, given that the person selected is a no evil eyebrow, so how many people were no evil eyebrows? 17. What is the probability that they are a yes taco tongue? 9. So in our calculators, we'll do 9 out of 17. It would be 0.529 or 52.9%. Now we're going to try to draw a conclusion about what this means for us and what this means about the events of taco tongue and evil eyebrow. If in theory, the two were not related in any sort of way, the probabilities that we just did in A and B would be the same percentage, because there really should be no reason why taco tongue affects evil eyebrow or evil eyebrow affects taco tongue. So these percentages should be the same, but are they the same? No. We have very different percentages, especially in this class, for what that means for our population. So our conclusion we can draw is the following. People who can do evil eyebrow are more likely to be able to do taco tongue. That's what ours says. We had 100% of the people that could do evil eyebrow still be able to do taco tongue. But we had 52.9% of the people who could not do evil eyebrow do taco tongue, which means there's some sort of relation there. We can tell by the numbers. Otherwise, these two events would be independent of each other. Now, do these actually affect each other? Probably not. There is something to do with like facial features being able to work together, but it's not like a cause and effect sort of thing. But two events are called independent. That's a vocabulary word for today. If knowing whether or not one event has occurred does or does not change the probability that the other event will occur. Again, because my probabilities for these two that we already did were not the same, we can answer the third question. Are the events yes taco tongue and yes evil eyebrow independent? No. Based on my numbers, they are not independent, because if we know someone can do evil eyebrow, it changes the likelihood they can do taco tongue. So these are no longer independent events, and their probabilities of combining them together get a little bit more complicated. Does that make sense?
Yeah.
Now, usually asking questions about whether something is independent or dependent is pretty straightforward, and we'll see that in the check for understanding part of the lesson. But let's dive a little bit more into these independent events once we can prove that they're independent and see how their probabilities change or are affected by each other. If two events are independent, then it makes calculating probabilities much easier on us. All we need to do is multiply the different probabilities together to find the probability that the two events can both happen. Games of chance are one of the best ways to explore this. So we're thinking like roulette, we're thinking like pick a card, any card, we're thinking like rolling a dice. Those are all games of chance. Today we're going to use a roulette wheel as an example. I'll be honest, I picked a really bad example of a roulette wheel to put in your notes because a typical American roulette wheel has the numbers 1 through 36 as well as 0 and 00, and the picture I gave you doesn't have 00. That's my bad. So I know, how dare I? So imagine there's one more on here that's a 00, and just like the regular 0, it would be green. That's what an American roulette wheel actually looks like. I don't know what I was doing with this clip art, but here we are. If that's the case, if we have a 000 and the numbers 1 through 36, how many total possible spots on this roulette wheel can the ball land in? 38 different spots. Do y'all know how roulette works? Yeah. So the dealer, the person running this game, spins this direction, and then they launch a little gold silver ball this direction. And eventually gravity starts to work, and instead of the ball continuing to go around this direction, it starts like and it lands in one of the spots. You win money based on guessing what kind of slot, I guess is what I'm looking for, the little ball falls into. You can bet on whether it's in a red, a green, or a black, and even an odd number, a specific number, all those sorts of things. So our first question says, what is the probability that the ball lands in the 11 spot? How many 11 spots on this roulette wheel are there? 1. There's only one 11 spot on this roulette wheel. That means there's a 1 out of 38 chance for this ball to land in the 11 spot. Again, the roulette wheel on your notes only has 37 spots. My bad. There should be a 00. If we throw that in our calculator, we'd get 0.026 or 2.6%. It's a pretty small probability. In fact, is it considered unusual for this to happen? Yes. Because it's less than 5% chance. Very good. Now, here's where the independence of this game comes in. We can assume each spin of the wheel is independent because where the ball lands on the first spin doesn't mean anything for where it lands on the second spin, correct? So each spin of the wheel is independent of each other. Part B says, what is the probability that the ball lands on the 11 spot 3 times in a row? So if we were doing this, all we have to do is multiply the 3 different odds together. 1 out of 38 over 1 out of 38 over times 1 out of 38. I think I said that weird, but you get it. Now, typing that in a calculator would be wildly annoying. Can we think of a more efficient way to type that in? 1 over 38 raised to the power 3, because we want this to happen 3 times. That's just a way more efficient way to type it in a calculator. Now, I want everybody to type this one in because something weird happens in your calculator and I want to discuss it. So everybody needs to type it in. Yeah, are you getting a weird looking number? I got a number when I did this in my calculator that was 1.82, and I lost the other numbers. 242, and then what does it say at the end? E. -5. Yes, E is times 10. This is scientific notation. And the fact that it says -5 means I'm going to move the decimal to the left, which you should naturally want to do, because can a probability be 182%? No, it can't be bigger than 100%. So you should have paused anyways and been like, wait a second, something's wrong. Notice then that it's scientific notation. That means this is actually 1, 2, 3, 4, 5. 0.0000 0.0018 or 0.0018%. Is that unusual? Very unusual, correct? Let's try another one. What is the probability that a single spin lands on a black spot? Oh, yes, Anna, let's go back. Okay, yeah, great question. The way I'm rounding on the notes, I'm rounding to 3 decimals because in general, that's what the book has been doing. But on a one like this, where it's clearly very, very small, they will tell you to round to like 5 or 6 decimals. So just pay attention to the little blue font underneath the homework that tells you how to round. It will change from question to question. Good question. Okay, sorry, let's go back to number C now. It says single spin lands on a black spot. How many black spots are there on here? There's 18. 18 times 2 is 36. And the numbers 1 through 36 are going back and forth, black and red. So there's 18 out of 38, which if we throw that in a calculator becomes 0.474 or 47.4%. Now, what if I wanted to find the probability of landing on black twice in a row? We'd raise it to the power 2, correct? Because I want to do 18 over 38 times 18 over 38, which is more efficiently written as 18 over 38 squared. Toss that bad boy into a calculator. What do you get? I got 0.224. Is that what you guys got? Which is 22.4%. The last question says, what is the probability that at least one of the next 5 spins lands on black? When you read a question and it says at least, this is a question you slow down on. This is a question you read carefully. Because technically, to answer this question with the tools that we have right now, we would need to calculate the probability that the first spin was black, the rest of the 4 were red. The first and second spins were black, the rest were red. First, second, third were black, the rest were red. What if the first was red, the second was black, and then the rest were red? Do you see how many options there are about to be for this? Like, no thank you, am I right? So instead of doing this, because at least is kind of crazy, what if we use the idea of the opposites, of the complements? What is the opposite of saying at least one? Remember, at least one means one or more. So what is the opposite of one or more? None. Because what's less than one? None. So what we can do is understanding, again, probability models have to add up to 100%. So if I was trying to find the probability of at least I'm going to do 1 minus the probability that none land on black. Because the words at least mean that number or more, we use the concept of probability models adding up to 100 or 1 to say, well, what if I just found the probability of this not happening and do 1 minus that probability? This, in general, is going to be a lot easier for us to find. So we add up all of the ones that are not black, which are the 18 red, and the 2 that are green, even though there's only 1 green on your picture, which means we are doing 1 minus 20 over 38. But how many times are we trying to have it land on not black? 5 times, which means I'm raising that probability to the 5th power. If we calculate the probability that none are black 5 times and do 1 minus that probability, we should get that the probability of at least 1 in 5 of these spins landing on black to be 0.960 once you round it, or 96%. Which makes sense to me, because if about half of this board is black, It's pretty high opportunity for me in 5 rolls for it to land on black. Again, when we see these at least probabilities, we slow down. We start to think about this in a creative way of how we can actually answer this question. Obviously, underneath that, we have all of our vocabulary today. Independent versus dependent events. Independent events, if the event of E does not affect the probability of event F, or vice versa for dependent. We discovered our multiplication rule, where if we have independent events, when we're trying to find E and F, we just multiply their probabilities together. Again, that's for independent events. If they're dependent, you do not do this. And if we have more than 2 independent events, like rolling the roulette wheel 5 times, we just raise it to the 5th power, or multiply all 5 probabilities together. Then we discuss the at least 1 probabilities. Remember, at least is your key word. Specifically when it's at least 1, those are the easier ones. At least is kind of troubling because there's so many ways it could be if you just need at least 1. So instead, we go ahead and use the probability, the complement of that probability, to solve. The probability that we find at least 1 is 1 minus the probability that we find none of whatever we're looking for. All right, let's do some check your understanding questions before we get back up to finish the whiteboard questions for 5.3. First part here, we're just going to decide if events are independent or not. Your first option is flipping a coin and rolling a die. Are those 2 independent or dependent events? Why? Yeah, they don't relate to one another. We would say the 2 do not impact each other. Me flipping a coin and me rolling a die are 2 totally separate events that don't influence each other. Knowing the outcome of one does not let me know anything about the outcome of the other. How about earning a bachelor's degree and making more than $100,000 per year? Independent or dependent? Why? They're dependent. Why are they dependent? Here's what I'm hearing in the mumbling. Having a degree can impact your ability to make money. Part C, independent or dependent. A randomly selected person from Texas and a randomly selected person from New York getting into separate car accidents in the same year. Independent, why? Say that, I just can't hear you. They're like 2 different states. The likelihood of one person in Texas getting into a car wreck, does that change the likelihood of somebody in New York getting in a car wreck? No. If they were maybe in the same city, we could say they might be dependent, because what if they get in the same car wreck? Or what if one car wreck causes the other one? But like Texas, New York, we're so far away. That's pretty much what we're going to say. One wreck doesn't cause the other. Last one, and you know I had to put this in here. Independent or dependent, completing all your homework assignments and getting a passing score on a test. They're dependent, y'all. Why? Because homework can help you do better on the test. And you know what? We're going to put the little... I'm doing this to you guys right now. Number 2 says the probability that a randomly selected 24-year-old male will survive the year is 0.9986 according to the National Vital Statistics Report. What is the probability that 3 randomly selected 24-year-old males will survive the year? Say it again. That to the power of 3. We're taking the probability of 1 24-year-old male surviving the year, and we're doing that 3 times because we're individually selecting 3 random males. Toss that into a calculator, please. we should have gotten 0.9958. We'll just round to 4 decimals for this one. Why did the number go down? Because we need all 3 of them to stay alive. It should technically be harder for that to happen, which means the probability goes down. If we increase this a little bit, what is the probability that 20 randomly selected 24-year-old males will survive the year? What do I do this time? To the power of 20. Because we're taking the same event and doing it 20 times, taking 20 randomly selected 24-year-old males. Toss that into a calculator. 9724, so 97.24%. Now, last question says, what is the probability that at least one out of a randomly selected sample of 1,000 24-year-old males will die during the course of the year? First of all, Spidey senses should go off because what did you read here? At least. So we pause, we slow down. We know we're going to end up using complementary probability when we see the word at least. And if we want at least one to not survive, when we're finding this probability, the probability that at least one does not survive the year, we find that by doing 1 minus none survive. Now, technically, our probability that we have in this question is telling us about the survival rate. But y'all, saying none do not survive is saying the same thing as all survive, which is the probability we know information about. So what we want to do to calculate this probability, since we're using complementary probability, is we do 1 minus the probability that a randomly selected 24-year-old lives, but we want that for all of the 1,000 people in this randomly selected group. Feels crazy to me that I'm making an exponent 1,000, but you are actually making that exponent 1,000. So in your calculator, please do 1 minus 0.9986 raised to the 1,000 power for the 1,000 people we want to survive the year. There is a 75.36% chance that we randomly select 1,000 24-year-old males and they make it through the entire year.